Hello there and welcome back to the Science Sleepy Minds. Above you, stars glimmer like scattered salt on black velvet. The silence is exquisite, like the universe itself is holding its breath. In front of you yawns a perfect sphere of shadow, utterly black, rimmed in ghostlight. That, dear traveller, is a black hole, and you're drifting toward it, slowly, irresistibly. There's no steering away now. You've crossed the event horizon, the so-called point of no return. From here on, every path, every option, every possible future ends in one place, the Singularity. You probably won't survive this, by the way. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And as always, drop your location and local time in the comments. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. There's no visible line in the sky to mark the event horizon, no flashing sign saying, "Abandon all hope, ye who enter here." But as you drift closer, you sense the change. The stars behind you warp, swirling into a luminous ring as light itself bends under the black hole's insane gravity. That distortion, like falling into a cosmic fisheye lens, is your first clue that things are no longer playing by the usual rules. In Newtonian terms, this region is where the escape velocity exceeds the speed of light. So unless you're hiding a warp drive in your back pocket, you're not going anywhere but down. Once you pass this threshold, no message, no signal, no photon of light can reach the outside universe. You've effectively been erased from existence as far as everyone else is concerned. Charming, isn't it? The event horizon isn't a solid surface, of course. It's a region, a boundary made of pure math. Kind of like an invisible toll gate that only charges you your entire future. And although we often think of it as a wall, it's more like a funnel-shaped edge stretched in every direction. You don't slam into it, you slip through it. Astronomers first gave serious thought to this gravitational horror show in the early 20th century, when Carl Schwarzschild solved Einstein's equations and accidentally created the blueprint for black holes. He didn't call them that. Honestly, the guy died before the implications were fully understood. But his Schwarzschild radius gave us the math behind this spooky edge of reality zone. That's the radius at which the escape velocity equals the speed of light, and every black hole has one, from the puny to the galaxy-sized. Historians still argue whether John Michell, an 18th century English natural philosopher, actually beat everyone to the idea. In 1783 he proposed dark stars so massive that even light couldn't escape. Not bad for a guy working before electricity was common. And here's your first fringe fact of the evening. In the 1970s, some researchers seriously discussed the possibility of creating artificial black holes using lasers. Just pop enough energy into a tiny space, and boom, your very own singularity. Don't try this at home. Unless you have, say, Jupiter's mass compressed into a golf ball and a serious grudge against physics. Now back to you, floating, helpless, calmly spiralling inward. You don't feel any sudden change, no lurch, no jolt. Crossing the event horizon doesn't come with fireworks, and, oddly enough, if the black hole is large enough, say, supermassive, you wouldn't even notice the exact moment you crossed it. Your spaceship's instruments would, but to your senses, just more darkness, and that quiet hum of inevitability. Here's a fun way to think about it. For everyone watching from outside, you're slowing down as you approach the event horizon. To them, it looks like you're crawling, your image dimming, stretching, freezing in place just before the edge. You become a ghost on the edge of space, red-shifted until you vanish. But for you, everything continues as normal, until it very much doesn't. It's a little like walking into a one-way mirror. The outside can see you right up until you vanish, but from the inside, you're already sealed off from the rest of the universe. No Wi-Fi, no exit, just you and the overwhelming pull toward a point where the laws of physics go to cry in a corner. You might wonder, does the black hole notice you? Does it hiccup when you fall in? Does the mass you add change anything? Yes, actually. Every time something crosses the event horizon, the black hole's mass increases ever so slightly. It's like a cosmic piggy bank for doomed matter. So congratulations, your final act is making a monster slightly more monstrous. Here's the kicker. The event horizon is just the beginning. Once you're past it, you're not just falling through space, you're falling through time. In fact, the roles of space and time get weirdly reversed inside. Moving forward becomes moving inward. You can no longer avoid the singularity than you can avoid next Tuesday. It's just your future now, and there's no turning back to Monday. Scientists still debate what's really happening at the event horizon. Is it smooth? Is it fiery? Is it just a math trick or a real tangible thing? The no-hair theorem says black holes are featureless apart from mass, charge, and spin. But some physicists suggest there might be structure. A fuzzball of tangled strings perhaps, or even an information-storing surface that remembers everything it consumes, like a cosmic calorie counter. And if this is making your head hurt good, that means your neurons are still functioning, for now. One last dreamy tidbit. If the black hole were spinning, and most of them are, the event horizon wouldn't be a simple sphere. It would be oblate, bulging slightly at the equator like a cosmic belly. And instead of a single boundary, you'd have two, an outer horizon and an inner one, separated by a region where you can, in theory, still dodge the singularity. For a little while, a gravitational purgatory, if you will. Don't get your hopes up, you're already inside, the sky's gone, ahead only deeper blackness. And gravity? It's only just getting started. You're not falling anymore, not really. Falling implies some choice, a direction you could maybe resist with a good jump or a tug on a rope. But here, now, past the event horizon, you're being unraveled, and not metaphorically. This is the place where the laws of physics twist themselves into knots, and you become, well, let's just say pasta metaphors are about to feel very personal. It starts slowly, too slowly to notice. The black hole's gravity isn't uniform. It's stronger at your feet than at your head, especially if you're falling feet first. That difference is tiny at first, barely a tickle in the cosmic force field. But as you move inward, closer and closer to the singularity, that difference becomes violent. It starts to stretch you, gently at first, like a tug, then harder, until your body elongates, vertebra by vertebra, organ by organ. Congratulations, you're being spaghettified. Yes, that's the real term. Spaghettification, also known as the tidal disruption effect, is what happens when the difference in gravitational force across your body becomes extreme. On Earth, tidal forces just make ocean waves and embarrass moon landing deniers, but in a black hole, tidal forces shred objects into strings of atoms. You don't fall in as a person, you fall in as a noodle. And here's a fun, horrible twist. If this is a stellar mass black hole, something just a few times heavier than our sun, you'll be shredded before you even reach the event horizon. That's right. In small black holes, the tidal forces are so intense near the boundary that they pull you apart before you even cross the threshold. But if it's a supermassive black hole, like the one at the centre of our galaxy, Sagittarius A star, you pass the event horizon in one piece. You'll feel the stretching later, deeper in, close to the singularity where the forces ramp up like a roller coaster you forgot to get off. Historians still argue whether the term spaghettification was coined by physicist Sir Martin Rees as a joke or a genuine attempt to make astrophysics delicious. Either way, it stuck. Because frankly, vertical gravitational gradient-induced atomic elongation just doesn't have the same flair. As you stretch, you might get the disconcerting sensation that your body is no longer one thing. Your head and feet experience time differently. If your feet are closer to the singularity, they move faster through space and time than your head. In a sense, they age faster, though trying to apply the word age here is like trying to measure soup with a ruler. There's something darkly beautiful about this stage. If you could see yourself, and really, thank heavens you can't, you'd appear as a glimmering strand of particles, longer and longer, thinner and thinner. The atoms that once made up your body, your skin, your teeth, your favourite hoodie, are strung into a cosmic thread, pulled toward the black hole's core like floss winding around the axis of doom. Here's a quirky historical tidbit. In 1969, physicist John Wheeler described a black hole as the ultimate elementary particle. He imagined matter collapsing into the simplest possible object, just mass, charge and spin. Everything else erased, hair gone, identity gone. But your spaghetti self, that's still part of the picture. Until the black hole finishes chewing, you're part of its swirling digest. Now don't worry, your atoms won't be lonely. As you're shredded, you might pass bits of other unfortunate objects. Satellites, wayward comets, old space stations, probably a few shoes. Everything the black hole has ever eaten is still technically inside, just compressed beyond recognition. You might find yourself sharing your final stretch with a 12th century scroll, a Russian space dog, or the remains of a Tesla Roadster. There's also a faint hope, one last absurd twist of physics, that your death might be kind of educational. Astronomers who observe stars being tidally disrupted by black holes get a fireworks show, X-rays flaring, gas spiraling, light bending in ways Einstein would have called cute. So your disassembly might light up the sky for someone, somewhere, sometime. But don't hold your breath. Or maybe do. It's not like lungs are going to help anymore. This process isn't instantaneous. If you could somehow watch your spaghettified self fall inward, you'd see your ends stretching farther apart, like taffy in slow motion. But inside the black hole, time doesn't behave the way it used to. For you, this might seem like moments or eternity. No one knows, because no one's come back to describe the ride. And what about your brain? The seat of consciousness, your inner monologue, the you reading this in a sleepy whisper? Well, if the stretching gets you before the radiation does, your neurons are torn into a line before they can complain. Some theorists say the brain couldn't possibly stay intact long enough for you to experience the full fall. Others argue there's a split second, just one, where your consciousness experiences time like never before, a final flash of forever. Historians still debate what happens to identity in the face of annihilation. Religion, philosophy and quantum physics all have their votes, and none of them agree. Is death a blink, a stretch, a merge with something larger? In a black hole, the question becomes less metaphorical and more physical. What is you when you're 10,000 miles long and one atom wide? Let's not forget the infallibly strange theory of frozen time perception. Some fringe thinkers speculate that, from your own point of view, time could slow down so much as you fall that the final moment stretches indefinitely, an infinite second, a personal eternity. Again, no one knows, which is a polite way to say probably terrifying. Before we close this section, let's float one last horrifying footnote. If you were falling with a friend, say a cozy sleep science companion, you'd lose sight of them not just because of distance, but because of physics. Light emitted from their direction might never reach you. Or worse, it might be redshifted so severely it stretches into radio silence. You're alone now, absolutely alone. But don't despair. There's something oddly peaceful about this next part. The stretching continues, but resistance fades. Your atoms, obedient as ever, keep marching toward their final arrangement. You're becoming part of something bigger, denser, weirder. Soon you'll reach the region where time stops pretending to be linear and space decides to fold in on itself. And all that stretching? That was just the warm-up. Time has always been a bit of a diva, showing up uninvited, refusing to slow down, aging your face even when you swear you've done nothing but drink water and mind your own business. But inside a black hole, time stops being merely inconvenient and becomes something far more disturbing. It stops being time at all, at least not in any way you're used to. You're still falling, or whatever verb best describes your journey now. The word fall is doing some very heavy lifting. At this point, you've been stretched like birthday taffy, and your body no longer resembles anything legally human, and while your atoms are still obediently heading inward, your sense of time is doing somersaults. For someone watching from the safety of the universe's sane outside edges, say an astronomer sipping lukewarm coffee, you're frozen. They see you moving slower and slower as you approach the event horizon, not because you're physically breaking, but because time itself is dilating. To them, you never truly cross that edge. You just get dimmer, redder, and weirder until you fade out of existence like a bad VHS recording. This is gravitational time dilation in action. The closer you get to a massive object, the slower time flows, relative to everything else. So the deeper you go into a black hole, the slower your clock ticks compared to the rest of the universe. And the math here is brutal. Even before you cross the event horizon, the difference becomes extreme. 1 second for you could mean hours, years, or millennia for someone outside. Historians still argue whether this phenomenon has philosophical implications, or if it's just relativity being extra dramatic. Einstein predicted it, of course. The man was good at making things weird. In his general theory of relativity, mass warp space-time and black holes are just the most extreme version of that. They don't just bend space-time, they fold it into a crumpled napkin, spill wine on it, and blame quantum mechanics. From your warped perspective, however, you're moving just fine. You pass the event horizon, you continue inward. You might even check your watch, if you still had one, and, wrists. Time still feels like it's moving forward. For you. But there's no you left to compare it to anymore. No outside reference. You're inside the cosmic isolation chamber now. There's an eerie comparison to be made here. In 1971, a Russian satellite reportedly experienced minor gravitational time dilation when it passed close to Earth's surface, just a fraction of a second difference measured with hyper-precise atomic clocks. That same effect, dialed up to apocalyptic levels, is what you're living through now. And here's a fringe theory to sprinkle into your spiral. Some speculative physicists think that if you were able to hang out just outside the event horizon, close enough to feel the time dilation, but not fall in, you could watch the entire future of the universe unfold in fast-forward galaxies colliding, stars dying, civilizations rising and crumbling. A whole Netflix series of the cosmos in the time it takes to blink. But you're already past that point. You didn't get the cosmic box seat. You got the backstage pass straight into oblivion. For a moment, if moment even means anything here, you might notice the world going disturbingly quiet. Not soundless exactly. Sound doesn't travel in vacuum anyway, but still. Like even the fabric of reality is holding its breath. As if you've entered a place where the concept of before and after has been revoked due to bad behaviour. This is where space-time does something especially devious. Inside the event horizon, the radial direction, inward, becomes time-like. That means moving forward in time is moving deeper into the black hole. You can't stop yourself, can't turn around, can't hover. Falling inward isn't just a physical direction, it's your destiny. You're not being dragged forward in space, you're being pushed forward in time, and your destination is singular. Get it? Singular? A quick historical detour to keep things spicy. In 1924, mathematician David Hilbert was already warning that the centre of a black hole, a singularity, wasn't just a math problem. It was a philosophical and physical emergency. He called it the end of space-time, which sounds suspiciously like the worst vacation spot imaginable. The idea of a singularity, a point where gravity becomes infinite and the known laws of physics collapse, first emerged from the Schwarzschild solution to Einstein's field equations. Initially, many physicists thought the singularity was just a mathematical oddity, a bug in the system. Surely nature wouldn't allow infinite density. But nature, as it turns out, isn't terribly interested in making sense to human brains. Back in your cozy interior death spiral, you may be thinking, wait, if time slows infinitely near the event horizon, Can I ever actually reach the centre? And here's where the math gives a snide grin. You reach it just fine. From your perspective, you hit the singularity in a finite amount of time. The whole spaghettified package, that long lonely noodle of matter you've become, hits the final destination in one uninterrupted timeline. Meanwhile, to anyone outside, you never quite get there. The paradox is baked in. From the inside, it's inevitable. From the outside, it's eternal. Some physicists have tried to resolve this with alternate theories. Maybe the singularity isn't real. Maybe it's replaced by a quantum fuzzball, or some kind of Planck-scale bounce that launches matter into another dimension. Fringe thinkers, and a few respected ones too, have even proposed that time doesn't really exist in the black hole core, that it becomes imaginary, a placeholder in equations that has no real meaning. And if your brain is melting trying to picture all this, welcome to the club. This is the exact spot where quantum physics and general relativity look at each other, shrug, and stop returning phone calls. Before we wrap up this time-bending interlude, let's chew on one last, lightly terrifying nugget. Some cosmologists believe that the final moments of falling into a black hole, when time slows infinitely, might feel like a frozen eternity. In those last microseconds, everything stretches. Light, thought, awareness. You don't die instantly. You might feel your fall for a long, long time, or you might blink out without knowing it. A brief twinge, a fade to black. Time won't tell. You're past the edge. You've been stretched like galactic chewing gum, and time is a mess of noodle-like confusion. But here's where things get really unfriendly. You're inside the event horizon now. The outside universe can't see you, and you can't send so much as a text message back. Light doesn't escape. Ideas don't escape. Even your best, wait what, expressions are swallowed up. But what makes this place so chilling isn't just the isolation. It's that physics itself, your trusty old friend, has stopped answering the phone. Space and time. They're not behaving the way you've been told they should. Inside a black hole, something strange happens. The axes of space and time switch. Like literally. What was a direction you could move through, like forward or backward, becomes your new timeline. And what was time, your forward march through seconds, minutes, and awkward high school memories, becomes just another spatial direction. You can't move away from the singularity any more than you can move backward through time. It's not just a suggestion, it's your new physical law. The singularity isn't a destination anymore, it's your future. You must go there. Every second that passes for you is another step closer. This idea is hard to visualize, and for good reason. Our brains weren't built to think this way. We evolved to dodge predators, find snacks, and occasionally look impressive at dinner parties, not navigate topologically inverted spacetimes, but that's exactly where you are now. A region where going deeper into space is going deeper into time. And here's something to casually lose sleep over, this interior geometry. It's not necessarily static. If the black hole is spinning, which statistically speaking it almost certainly is, the entire interior could be rotating. Not just the matter, space-time itself. You're not just falling into darkness, you're swirling in a twisted funnel of causality where space-time behaves like a drunk ceiling fan. This spinning distortion creates what's called an ergosphere outside the event horizon. Inside, it warps things even more. Imagine trying to walk across a river where the current gets faster the closer you get to the middle. Eventually, no matter how hard you try, you're swept in. The rotating black hole's version of that. You're dragged by frame dragging, an effect predicted by Einstein and proven decades later by the Gravity Probe B mission, which confirmed space-time does swirl near massive rotating bodies. Inside the event horizon of a spinning black hole, what we call a Kerr black hole, you may encounter more than just a singularity. The math predicts something even stranger, a ring singularity and possibly a Cauchy horizon, another boundary that separates regions of cause and effect. Cross that, and you might not even know what before and after mean anymore because might follow effect, or precede it. or tie it into a decorative knot and hang it on a wall. Historians still argue whether the Kerr solution is physically real or just a very shiny math toy. Some believe these features are unstable, that any matter falling into the hole will destroy the exotic internal structure before it has a chance to really exist. Others suggest that if the inside of a rotating black hole does exist as theorized, it might contain portals to other universes, wormhole passages, or time loops. But all of that remains purely theoretical, cloaked in uncertainty and the occasional angry chalkboard. Let's toss in a fringe theory, just to spice things up. There's an idea floating around, controversial and not widely accepted, that the singularity inside a black hole might not be a point at all. Instead, some models propose that space is infinitely curved, but the curvature is distributed over a surface rather than concentrated in a single point. So instead of hitting a dot, you slam into a wall of broken reality. Isn't that comforting? But back to your current predicament. Inside the horizon, reality bends into a funnel. No matter what you try to do, your future is fixed. You're heading for the singularity and nothing. Not rocket boosters, not the power of love, not even Christopher Nolan can help you now. Here's the twist though. Even though you're falling toward this singularity, it might not look like anything at all. It's not a glowing pit or a fiery center. It's a place where the math breaks, where quantities like density and gravity curve to infinity. You might pass a certain radius where your instruments stop functioning, where all attempts to measure anything just spit back static. This is the point where physicists start using phrases like geodesic incompleteness and metric breakdown, which is their way of saying we have no idea what's going on. It's not just that our measurements stop working, it's that the very idea of measurement ceases to be meaningful. There's no distance, no time, no anything, just the raw, unfiltered finale of existence. And despite all our fancy telescopes and particle colliders, we've never seen inside a black hole. We know what they do. We can detect their influence on stars, gas, light, even space itself. But what happens after you cross the threshold? That's pure theory. A backstage area no one has ever returned from. Let's drop a quirky historical fact here. In the 1990s, physicist Kip Thorne and colleagues explored the idea of using black holes as gateways for time travel. Their work inspired the film Interstellar, where a character falls into a black hole and ends up behind a cosmic bookshelf whispering data through time realistic. Not remotely. But based on actual math? Weirdly, yes. Still, in reality, falling into a black hole isn't a ticket to a narrative arc. It's a one-way trip into a region where your concept of where and when stops being meaningful. You're not dying in the way we typically understand it. You're transitioning into a kind of existence that current physics isn't equipped to describe. So now you fall, not through space, but through fate. Time no longer flows past you. It's a gravitational chute dragging you downward. The singularity is no longer a place you approach. It's an event you must reach. Every moment is just one more sliver of your journey into a point that, as far as our science knows, doesn't even have volume. And there's nothing left to do but go there. You are falling into a place that isn't a place. A destination that exists only because our equations break and can't stop coughing up infinity. It's the end of your journey, or perhaps the end of any journey, because once you arrive here, the concept of journey itself has no meaning. You've reached the singularity. Or rather, the singularity has reached you. But here's the problem. No one knows what a singularity actually is. All we know is that it's the mathematical result of gravity compressing matter to an infinite density and zero volume. Yes, zero. It's the divide by zero moment of the universe, and it's very much not okay. From your perspective, as your elongated particle stream slips closer, the singularity doesn't appear as a point to aim for. It's your future. Just like tomorrow used to be a date on your calendar, the singularity is now your destiny. You're not travelling toward it. You're moving through time, and the singularity is where your timeline terminates, like the season finale of you. In non-spinning black holes, the idealized kind called Schwarzschild black holes, the singularity is a single point at the very center. But in more realistic spinning black holes, Kerr black holes, the singularity may take the form of a ring, a twisted rotating loop where space-time tears itself apart in style. And here's where it gets weird. Well, weirder. According to certain solutions to Einstein's equations, this ring-shaped singularity might not be the end of your story. It might be a kind of portal you could pass through it, if you're lucky or made of math, and emerge somewhere else. Another place in our universe, or another universe entirely. This is where science fiction makes itself at home. The idea of wormholes, shortcuts through space-time, often links directly back to the properties of rotating black holes. The math allows for it. The universe, however, remains suspiciously silent on whether it actually does it. Historians still argue whether Einstein and Rosen's 1935 paper on bridges in space-time, what we now call Einstein-Rosen bridges, was meant to describe physical reality or just a neat trick of math. But ever since, the notion has lingered. Maybe black holes aren't endings. Maybe they're doors. Back to your doom noodle. The real singularity, assuming it exists in the way general relativity predicts, is not a physical object you can see, touch, or experience in any traditional sense. It's not like falling into a pit and hitting a wall. It's more like the moment a calculator gives up. The values for gravity, curvature, and density reach such absurd levels that our physical theories produce nonsense. Your mass, energy, quantum state, everything that once defined you, is squeezed into the ultimate summary, a single point of information. Or maybe not. Here's where the quantum rebellion begins. According to quantum mechanics, no information in the universe can ever be truly lost. Every particle has a history, a fingerprint, a record of where it's been and how it's interacted. But black holes? They gulp things down, reduce them to mass and spin, and seemingly erase the rest. This leads to what's called the information paradox, a debate that has tortured physicists for decades. Stephen Hawking once argued that the singularity destroys information, violating quantum theory. Later, he backtracked and suggested that information might be scrambled and leaked back out via Hawking radiation. We'll get to that delicious thought later, but the debate is far from over. The question remains, when you hit the singularity, does everything you are simply vanish? Or is there some record, some trace left in the universe's accounting ledger? Quirky fact break. Roger Penrose, who worked closely with Hawking, earned a Nobel Prize in 2020 for proving that the formation of singularities is an inevitable outcome of general relativity. Given a big enough collapse, he also proposed that singularities might not be the end, but instead a boundary to something deeper. He even co-developed the idea of conformal cyclic cosmology, where our universe is just one of many that arise after each other through these cosmic resets, a literal universe afterlife. But here's the less glamorous version. In practical terms, the singularity is where your spaghetti thread of atoms ends. It's not a bang, not even a whisper, just a fade. 1 second you're falling, the next you are undefined. If we could observe you, if we could watch this whole journey, there would be no splat. Your descent slows to a halt from the outside, from the inside. It completes in a finite tick of time. And then, in current models, that's it. Unless it's not. Some physicists believe the singularity is simply a sign that general relativity is incomplete, that the equations stop working is not because nature breaks, but because our understanding does. This has fueled a search for a theory of quantum gravity, a framework that unites the smooth curves of relativity with the jittery chaos of quantum mechanics. Among the top contenders is string theory, which proposes that the fundamental building blocks of reality aren't particles, but tiny, vibrating strings of energy. According to some string theorists, the singularity doesn't compress to a point. Instead, matter reaches a minimum possible size, the Planck length, beyond which compression is impossible. Reality itself becomes grainy, and the singularity is replaced by a cloud of exotic physics that we simply don't understand yet. Another wildcard theory, loop quantum gravity, which posits that space is quantized, made up of tiny loops woven together like a cosmic chainmail. This theory suggests that instead of being crushed to nothing, matter could bounce, rebound outward into a new space-time region. In other words, the singularity becomes a bounce point, potentially birthing a new universe on the other side. Of course, these ideas are still deeply theoretical. We can't test them. We can't peer inside a black hole to check. All we have are equations, simulations, and extremely patient blackboards. But if the singularity is the end, if it truly erases information and scrubs the slate clean, then you've just participated in the greatest disappearing act in the cosmos. You've contributed your mass to the black hole's gravity, your angular momentum to its spin, and your existence to its mystery. You are a spark in the void, a flash of awareness, and now you're part of the deepest riddle the universe has to offer. So let's say you've finally reached the singularity. Congrats on making it to the most physically confusing and philosophically unfriendly location in the known universe. But just before we wipe your existence clean from cosmic memory, let's consider an alternate fate, one that involves less silent annihilation and more screaming firewall. Enter the firewall paradox, a concept that sounds like it belongs in a cybersecurity class, but actually comes from some of the brightest minds in theoretical physics trying to answer one question. What really happens when you fall into a black hole? See, up until now, we've been kind of gentle with the idea. We told you that you'd pass through the event horizon without noticing, that your atoms would quietly stretch into spaghetti, and that your final moments would be more philosophical than physical. But in 2012, a team of physicists threw a flamethrower at that idea, figuratively. They proposed that instead of a calm, uneventful crossing, you'd encounter a firewall, a region of intense, catastrophic energy right at the event horizon. As you fall in, instead of slipping quietly into the void, you'd slam into a wall of high-energy particles that would vaporize you instantly. Not exactly the graceful fade-out we'd been romanticizing. This was all part of the now infamous AMPS paradox, named after physicists Almheri, Marolf, Polchinski, and Sully. They suggested that preserving the principles of quantum mechanics, specifically the rule that information cannot be destroyed, requires there to be some sort of energetic breakdown at the horizon. In short, to save quantum theory, you might have to kill off general relativity's smooth, comfy vision of black hole interiors. Historians still argue whether this theoretical firewall is a real phenomenon or just a byproduct of incomplete math. Hawking himself wasn't a fan of it. Others are more open-minded, and some naturally think it's all quantum nonsense being taken too literally. Let's pause here and do a quick recap of what's being wrestled over. 1. General relativity says the event horizon is not a place of drama. If you fall in, you wouldn't even notice it. That's the nice version. 2. Quantum mechanics says information can't be lost. Ever. 3. But when a black hole eats something, it seems to erase all the information except for mass, spin, and charge. 4. And if the black hole eventually evaporates via Hawking radiation, where does the information go? 5. The firewall hypothesis says maybe the event horizon is not smooth. Maybe it's where information gets violently scrubbed and your atoms get quantum blasted into oblivion. Charming. If the firewall exists, it would mean that the smooth transition we've been describing is an illusion. Instead of your atoms quietly crossing into darkness, they'd be incinerated at the surface. Your information wouldn't fall in, it would be annihilated or stored right there. The interior of the black hole might not even be real in the traditional sense. It could be a kind of cosmic hologram, projected but never actually accessible. Here's a fringe idea to toss into the fire, pun fully intended. Some researchers suggest the firewall is a metaphysical alarm bell, not a real physical phenomenon, but a sign that our current theories are deeply incompatible. That is, the fact that these laws conflict this badly tells us something is broken at a foundational level. It's not about choosing one theory over another. It's about accepting that we're still clueless about what's really going on at that horizon. This leads us to another playful twist on the whole thing. What if there's a firewall only sometimes? Some speculative models propose that whether or not you hit one depends on how the black hole formed, how quickly it's evaporating, or even your own quantum state. So your trip into a black hole might be a quantum gamble. You either slide in silently, or get disassembled by the universe's angriest laser grid. Now let's take a moment to appreciate how frustrating this is for physicists. They've spent a century building two beautiful, elegant frameworks: general relativity, which governs the very big, and quantum mechanics, which rules the very small. Both work fantastically well in their own realms. But black holes, they are where the two theories are forced to shake hands, and instead of a warm greeting, we get paradoxes, firewalls, and a burning question mark hovering over reality. Quirky historical tidbit. The idea that the event horizon is a membrane of sorts dates back to the membrane paradigm developed in the 1980s. In that view, the black hole's surface behaves like a hot electrically charged membrane that records everything falling into it. It doesn't resolve the firewall issue, but it does give the event horizon some properties, like viscosity and electrical resistance, that make it feel more alive. Like the black hole isn't just a hole, but a surface that does stuff. According to this model, your information might not fall into the singularity. Instead, it might be smeared across the event horizon like cosmic frosting, slowly being radiated back into space over eons via Hawking radiation. A slow drip, drip, drip of quantum secrets. So what does this mean for you, dear spaghettified traveller? Well, if the firewall is real, you don't make it very far. Your particles hit the wall and are obliterated into quantum noise. The idea of stretching gently into the singularity becomes moot. You don't get the chance. If the firewall isn't real, you go on falling, broken apart more by gravity than by heat. Either way, your days of coherent thinking are numbered. There's a darker implication here too. If firewalls are real, then black holes don't just erase you. They erase space and time themselves beyond the boundary. They become truly final. Not mysterious interiors with strange geometry, but dead ends, glitch zones, annihilation hubs. And yet, physicists haven't reached consensus. Theoretical work continues. New proposals surface, trying to reconcile the contradictions, like ER equals EPR, a bizarre idea suggesting that wormholes and quantum entanglement are actually the same thing. Yes, that's coming later. For now, we leave you poised at the edge of certainty, right where the event horizon used to feel like a soft boundary, until someone lit it on fire. So the next time someone tells you falling into a black hole would be peaceful, just a quiet slide into oblivion, remember this little wrinkle. It might also be the most energetic, brain-melting death imaginable, vaporized by information itself. Destroyed not by matter or motion, but by the fundamental laws of how reality tries and fails to remain consistent. Sweet dreams. At this point in your deeply unfortunate journey, you've flirted with the idea of being shredded, slow-cooked by time, crushed into a singularity, and possibly flash-fried by a theoretical firewall. And you're still wondering, how can a thing that's literally called black emit anything at all? Well, welcome to the part where the universe goes full paradox again. Because yes, black holes do leak. They aren't entirely black, and the reason for that slow leak is one of the most astonishing, delightful, and profoundly unsettling ideas ever proposed in theoretical physics: Hawking radiation. Let's set the scene. It's 1974. Stephen Hawking, British physicist, wheelchair-bound icon, and master of blowing everyone's minds, is staring at black holes through the lens of quantum field theory. Up to that point, the understanding was simple. Black holes eat everything, let nothing out, and just grow bigger and scarier over time. But Hawking asks, what happens if we throw quantum mechanics into the mix? Spoiler, the answer is weird. According to quantum theory, empty space isn't actually empty. It's teeming with so-called virtual particle pairs of particles and antiparticles that blink into existence for the briefest micro-instant and then annihilate each other almost immediately. They're like reality's pop-up ads, constantly appearing and vanishing just as quickly. But at the edge of a black hole, the event horizon, things get funky. If one of these particles happens to appear right at the horizon, one particle might fall into the black hole while the other escapes into space. Normally, they'd cancel each other out, but this separation breaks the rules. The escaping particle becomes real, detectable, energetic, and the one that fell in is lost, reducing the black hole's total energy just a smidge. And energy, of course, is mass, so the black hole shrinks ever so slightly. Hawking realised that this process would cause black holes to radiate, very slowly, very subtly, over unimaginable stretches of time, thus Hawking radiation. It's like a cosmic drip leak, with the black hole slowly losing mass until eventually it evaporates entirely. Yes, black holes can die. Historians still argue whether Hawking initially believed his own result. It contradicted decades of gravitational dogma, suggested black holes weren't eternal, and caused immense headaches for everyone trying to reconcile this with general relativity, but it held up. Over the decades, it became one of the cornerstones of quantum gravity research. Even though we've never observed Hawking radiation directly, it's just too faint to detect in the wild. Yet, let's put this in perspective. For a stellar mass black hole, the rate of radiation is almost laughably small. We're talking one photon every few billion years. It's not exactly a fireworks display, but the smaller the black hole, the faster it radiates. In fact, if you had a tiny black hole the size of, say, a mountain, it might evaporate in a dramatic burst of gamma rays, and if it were even smaller, say, the mass of a skyscraper condensed into a subatomic point, it would vanish in a snap, releasing enough energy to ruin everyone's afternoon. Which brings us to a fringe thought: primordial black holes. These are hypothetical baby black holes that might have formed right after the Big Bang, some small enough to be evaporating right now. Some physicists have even proposed that sudden bursts of gamma radiation observed in deep space could be the death size of these ancient miniature monsters. But back to you. You're falling into the black hole. You're wondering what this outward radiation has to do with you. After all, you're not a virtual particle. You're just a noodle-shaped ex-human, drifting steadily toward a mystery. Here's the twist. Hawking radiation might be leaking your information out of the black hole, or it might not. This is where the infamous information paradox rears its head again, because quantum mechanics says that information can't be destroyed, ever, not even by a black hole. But if black holes evaporate and vanish, and the Hawking radiation that escapes is completely random, then where did your information go? Your thoughts, your particles, your entire molecular autobiography? Did it vanish forever? Some physicists argue that the radiation somehow contains the encoded remains of everything the black hole ever consumed, that the black hole's surface remembers and releases it slowly, kind of like a cosmic hard drive doing a long laggy upload. Others believe the information is stored holographically on the event horizon itself, like a 2D record of a 3D event. This is part of the famous holographic principle, which we'll get into soon, but here's the teaser. The idea that everything inside a black hole is encoded on its surface. You're not falling into the abyss. You're being saved as a flat file. Then there's the truly strange option, that black holes don't evaporate completely. They leave behind a remnant, a tiny, stable, information-packed core that just sits there forever, containing all the data the black hole ever consumed. It doesn't radiate, it doesn't grow, it doesn't shrink. It just exists, like a cosmic USB stick nobody knows how to plug in. Quirky fact break. Hawking once bet fellow physicist John Preskill that information was lost in black holes. Years later, Hawking conceded, grudgingly, and presented Preskill with a baseball encyclopedia as a symbolic return of lost information. Physics. Come for the paradoxes, stay for the passive-aggressive gifts. But here's the kicker. The physics community still hasn't resolved the paradox. Despite decades of equations, simulations, and angry conferences, no one knows exactly how, or if, black holes preserve information. You, unfortunately, are now part of the experiment. As your atoms fall deeper, perhaps they're being recorded, perhaps they're being scrambled and released, photon by photon, into the cold, ancient dark, or maybe they're gone, utterly and forever. There's no firm answer, only competing theories and a growing sense that something fundamental about the universe remains out of reach. So yes, black holes leak, slowly, elegantly, and with every wisp of Hawking radiation, the cosmos reminds us that even the darkest, densest things can't keep everything to themselves. Eventually, even monsters must fade. Let's talk about secrets. Your secrets, to be specific. Everything you've ever done, thought, touched, eaten, regretted, or binge-watched. Now imagine tossing all of that into a black hole gone, right? Erased forever, except that shouldn't be possible. According to quantum theory, information, meaning the full, precise state of every particle involved, can't be destroyed. Ever. Not even if you and your entire messy human history are hurled past an event horizon, turned into quantum spaghetti, and compressed into an atomic whisper. This core tenet of physics is why the information paradox has kept brilliant minds up at night for decades. So, what really happens to your information once it's inside a black hole? Let's rewind slightly. You, the brave hypothetical astronaut, have long since passed the event horizon. Your body is no longer a body, your atoms are somewhere in the black hole's gut, and time has essentially become a downhill slide into a singularity-shaped pit of doom. From a classical physics perspective, you're gone, completely. What the black hole now knows about you is frighteningly minimal. Your mass, your electric charge, if any, and your angular momentum. That's it. This idea is called the no-hair theorem. In simple terms, it says black holes have no hair, no distinguishing features. They're perfectly bald. No matter what falls in, the hole just grows a little heavier, maybe spins a bit faster, but it forgets all the juicy details. You could throw in a copy of Shakespeare, a hippo, or your favourite embarrassing playlist. It all ends up as blandly uniform mass and spin. But here's where the paradox kicks in. Quantum mechanics insist that if you know the final state of a system, you should, in theory, be able to work backward and figure out the initial state. So if black holes erase the fine-grained information of everything they devour, the rules break. You can't rewind the tape. The universe loses track of who did what, and that is a huge problem. Physicists have tried everything to resolve this. Some, like Hawking in his early years, argued that maybe information really is destroyed. That's the price of having a singularity. It's a dead zone of logic and law. But this suggestion makes quantum mechanics extremely cranky, and most of modern physics is built on quantum mechanics being right. Others believe that the information is somehow preserved, but how is the million-dollar question? Or rather, the how has about a dozen competing answers, each one weirder than the last. One of the frontrunners is the holographic principle, which we'll get to in more depth next. But for now, here's the preview. It suggests that all the information that falls into a black hole isn't destroyed, but is instead stored on the surface. The event horizon itself, like data etched into a galactic vinyl record. So instead of disappearing, you become a kind of hologram. Not you as you remember yourself, of course. More like a quantum-encoded echo of you, your mass, your entropy, your atomic quirks, all recorded in the surface area of the black hole. Not the volume, the surface. But wait, there's more. A strange twist comes in when you consider black hole complementarity, a proposal that basically tries to have it both ways. From the perspective of someone outside the black hole, all your information is smeared across the event horizon and slowly radiated back out through Hawking radiation. But from your perspective, falling in, you sail smoothly past the horizon and go splat at the singularity. Both versions are true, but they're mutually inaccessible. It's like the universe is running two different realities side by side, and no one can compare notes. Historians still argue whether this counts as a satisfying solution or just a clever way to dodge the math. Because what's being proposed here is a kind of observer-dependent reality. A universe where truth depends on where you're standing. Einstein might have raised an eyebrow. Schrödinger would probably just sigh loudly. Let's now sprinkle in a fringe favourite, the final state projection hypothesis. This one's a doozy. It suggests that instead of information being destroyed, it's reflected at the singularity, like bouncing off a metaphysical mirror. Every infalling particle gets tangled into a final quantum state that then influences the Hawking radiation, escaping the black hole. So in a very non-intuitive way, your info does get out. It just takes a cosmic detour through the end of time. Needless to say, this idea has a hard time proving itself. Meanwhile, there's growing support for the view that information comes out, scrambled beyond recognition, in the Hawking radiation itself. Each photon that leaks from the black hole carries some microscopic piece of the puzzle, and given enough time, trillions of years mind you, all the information could eventually be recovered. The problem is that this process would be insanely slow. A black hole formed from one solar mass would take around 10 to the 67th power years to evaporate. That's more zeros than your bank account will ever see. And even if it does emit your information particle by particle, it would be so garbled that reconstructing it would be like rebuilding a library from ashes and static electricity. Here's a quirky and rather haunting analogy. Imagine writing your entire life story in glitter, dumping it into a hurricane, and then trying to reassemble the book from the scattered specks 10 billion years later. That's roughly how challenging it would be to recover personal data from Hawking radiation. Still, some physicists remain optimistic. They point to unitarity, a principle in quantum mechanics that says information is never lost, only transformed. If black holes violate unitarity, the whole framework of quantum theory may collapse. So for the sake of everything else in physics, information must survive, somehow. And in 2019, a new breakthrough arrived in the form of quantum extremal surfaces and the calculation of page curves, a mathematical tool that suggests information really does come back out of evaporating black holes in a way that restores unitarity. It's complicated, elegant, and deeply satisfying if you speak fluent tensor calculus. If you don't, well, you'll just have to trust that smarter people are panicking slightly less than they were 10 years ago. So where does this leave you, our loyal noodle-fied protagonist? Your secrets might not be lost after all. They might be out there, encoded in photons dancing across the universe. Or they might be smeared on the event horizon like the most tragic bumper sticker in history. Or maybe, just maybe, the singularity gave you one last quantum kiss and whispered your essence into the void. Either way, the universe isn't finished arguing about you. You're now two places at once, or rather your information might be. On the one hand, you're somewhere deep inside the black hole, beyond the event horizon, stretched, scrambled, and headed for the singularity. On the other hand, your information may not have made it all the way in. It could be smeared across the outside surface of the black hole, encoded in a weird, two-dimensional whisper. This isn't science fiction. It's the foundation of one of the most startling ideas in theoretical physics, the holographic principle. Let's start with a mental image. Picture a hologram, a two-dimensional surface that, when illuminated properly, reveals a three-dimensional image, like those shiny stickers that used to come with trading cards, or those magic postcards that look different when you tilt them. That's a basic analogy. Now apply that concept to the entire universe. In the 1990s, physicists Gerard 't Hooft and Leonard Susskind began developing a radical idea. that all the information contained in a volume of space could be represented by data on its boundary, not just for black holes, for everything. In other words, your 3D self may actually be a 2D projection. You're a very convincing illusion, backed up by math so complicated it makes most calculators beg for mercy. But black holes were the testbed for this concept. Back in 1973, Jacob Bekenstein had already noticed something odd. The entropy of a black hole, the measure of how much information it could contain, didn't scale with its volume like most things in the universe. It scaled with its surface area. That is, the larger the area of the event horizon, the more information the black hole could hold. That's not how we normally think. A box of books holds more books the bigger it gets inside, not based on how much wallpaper you'd need to wrap it. But black holes? They only care about surface area. The event horizon becomes the ultimate scoreboard of everything the black hole has consumed. And here comes the weird part. This surface might actually contain all the information necessary to describe the entire black hole interior. Not just what fell in, but every single quantum property of every bit of matter and energy that's ever passed the boundary. It's all there encoded, trapped, waiting. So what does that mean for you? Well, as your body stretches into subatomic string cheese inside the event horizon, your data might be projected in perfect but unreadable detail onto the surface. The version of you inside keeps falling, but the version of you on the surface is frozen, locked in time like a tattoo on the skin of space itself. Think of it like this. You fall into the black hole and disappear, but an ultra-compressed shadow of you is stamped onto the surface. No one can read it, no one can recover it, but it's there. Maybe forever, maybe until Hawking radiation spits it back out. Historians still argue whether this principle is a true feature of nature, or just an extremely clever mathematical trick. But the idea got a huge boost in 1997 when physicist Juan Maldacena proposed the ADS/CFT correspondence, a highly technical theory, don't worry, no quiz at the end, that basically showed how a gravity-filled universe in higher dimensions could be fully described by a quantum theory on a lower dimensional boundary. Translated, a universe with gravity can be equivalent to a universe without gravity, so long as the information is stored holographically on a surface boom. And now physicists are left to wonder, is this just how reality works? Are we living in a projection? Is space-time itself a byproduct of entangled quantum information smeared across a boundary we'll never reach? Chew on that while you fall. Let's bring this down to black holes again. The holographic principle tells us that instead of erasing information, the black hole event horizon becomes a storage device, a vault. Every time something falls in, the black hole records it, not inside, but on the boundary. This might be how the universe gets around the no-hair theorem. You don't need hair if all the details are shaved off and filed neatly at the edge. Here's a fringe twist. Some theorists propose that space-time itself may emerge from the entanglement of quantum information stored holographically. That is, the volume inside a black hole isn't a real, separate region. It's just the appearance of space arising from patterns on the surface. So if you think of your journey into the black hole as a real descent through a real place, it might be an illusion. What's actually happening could be a kind of quantum computation playing out on the boundary. The you falling inside might not even be in a real inside. It might just be a program running on the black hole's outer shell. A quick historical aside to lighten the existential blow, this all came to a head in the late 20th century as physicists tried to resolve the black hole information paradox. Leonard Susskind famously clashed with Stephen Hawking for years, trying to prove that information wasn't lost. Eventually Hawking conceded, sort of, and acknowledged that maybe, just maybe, black holes don't destroy information after all. So what does this mean for the very concept of place? In a holographic universe, location might be relative. You might be inside a black hole, but also preserved on its surface. The information describing you might not move anywhere, It might just transform into another format, like uploading your brain to a cosmic cloud server made of geometry and regret. Let's add one more oddity. If reality is holographic, and black holes are the clearest example of this, then it's possible every region of space works this way, that your living room, your favourite coffee shop, and your awkward middle school memories are all encoded on the boundary of some larger dimensional space-time. Yes, you might be a hologram, but a very high-resolution one. No one's accusing you of being pixelated. In the end, what the holographic principle does is turn our whole understanding of black holes, of gravity, of space, of information, inside out. And it offers a possible way to resolve the greatest paradox in modern physics: how to reconcile the destruction of information in black holes with the unbreakable rules of quantum mechanics. So even though you've fallen, stretched, evaporated, and possibly been flash-fried by a firewall, you might not be lost. Not entirely. A version of you, an imprint, is still out there, etched into the very fabric of a black hole's horizon. Your data now. Elegant, encrypted, and utterly unreadable. So far you've been swallowed, stretched, frozen, theorized, and maybe even immortalized as a cosmic QR code on a black hole's surface. That alone should earn you a few points with the universe, but what if, just maybe, you're not done yet? What if, instead of being lost forever or slowly radiated away as hawking fog, you get spit out? Welcome to the strange and speculative world of white holes, the cosmic reverse Uno card to everything we've learned so far. Let's start with what a white hole is. If a black hole is an object that lets nothing escape, not light, not matter, not even your deepest regrets, a white hole is an object into which nothing can enter. Instead, it only expels matter and energy, constantly, like a cosmic vending machine stuck in refund mode. In theory, a white hole is the time reverse of a black hole. Everything a black hole swallows, a white hole would eject. If that sounds impossible, it probably is. But in the world of general relativity, where time and space can bend, twist, and flip, it's at least mathematically allowed. General relativity doesn't care what direction time flows. It works fine either way. So, if you run the equations for a black hole backward, you get a white hole. Historians still argue whether Einstein and Rosen's famous 1935 paper, yes, the one that gave us Einstein-Rosen bridges, truly meant to suggest that white holes could be real. Their math certainly left the door open. But at the time, everyone was still too stunned by the idea of black holes to consider a mirror opposite. But if they did exist, what would a white hole actually look like? Imagine a region of space that violently ejects energy, radiation, and possibly even matter, but which you can never approach. Try to fall in, and space-time itself kicks you away. It's like an upside-down waterfall. Instead of pulling you in, it pushes you out. Hard, permanently. The problem? We've never seen one. No telescope has detected anything that fits the profile of a white hole. And since they'd be absurdly bright and unstable, you can't keep spewing matter forever without consequences. Their absence in the observable universe is a bit of a clue, so most physicists treat white holes as purely theoretical creatures, interesting in math, but unlikely to exist in our messy, entropy-loving cosmos. But that hasn't stopped some from dreaming. Here's where your black hole journey gets a possible sequel. According to certain speculative theories, what falls into a black hole might not vanish entirely. Instead, it could emerge elsewhere, somewhere through a white hole. The idea is that black holes and white holes might be connected, like tunnels through space-time. And yes, this is where wormholes enter the chat. A wormhole, or Einstein-Rosen bridge, is a hypothetical tunnel connecting two separate points in space and time. Imagine folding a piece of paper so two distant points touch, poke a hole through, and you've got a shortcut. If black holes are the entrance to this shortcut, then white holes might be the exits. That means you, our unlucky falling traveller, might not be doomed. You might instead be transported. Maybe not alive, maybe not recognisable, but moved nonetheless. There's even a fringe idea that our entire Big Bang was actually the eruption of a white hole. In this model, A black hole in a parent universe collapsed and funneled its contents into a new space-time bubble, ours, meaning the singularity that created our universe could have been someone else's cosmic garbage chute. Talk about recycling. The most speculative version of this, brace yourself, is that every black hole creates a new universe inside it, a kind of cosmic nesting doll, where each singularity is a seed, spawning new dimensions, new physics, maybe even new life. And white holes? They're the sprouting end of that process. But let's dial it back for a moment. There are a few major problems with white holes actually existing in any literal sense. 1. Stability. A white hole, by definition, would explode with energy. That's not just poetic, it's physically catastrophic. Any tiny disturbance could collapse the system. It would be wildly unstable and short-lived. 2. No formation mechanism. While we know, or think we know, how black holes form from the collapse of massive stars, there's no accepted process for creating a white hole. You can't just throw matter out of nowhere, unless again it comes from another universe. Third violation of entropy. The second law of thermodynamics tells us that entropy, the universe's measure of disorder, must always increase. White holes decrease entropy, at least locally, by taking in chaos and spitting out order. That's deeply offensive to physics as we know it. But the math? Oh, the math loves white holes. They're beautiful, symmetric and elegant. And in science, elegance is often an invitation to dig deeper. Let's sprinkle in a historical curiosity. Russian physicist Igor Novikov once proposed the white hole time machine idea. According to his model, white holes could serve as the exits to wormholes that allow time travel. But there's a catch. You can't go before the wormhole existed. So the past is safe from paradoxes. Probably. And in more modern times, some loop quantum gravity models suggest that, instead of hitting a singularity, matter inside a black hole undergoes a bounce, a quantum bridge that avoids infinite density and re-expands on the other side. Where? Into a white hole. When? That's trickier. In these models, your fall might take milliseconds from your perspective, but billions of years could pass on the outside. You might emerge through the white hole in a distant future, in another region of space, or perhaps into a universe with different physical constants altogether. If that's true, well, congratulations. You just became a sort of cosmic traveller. Not a conscious one, perhaps. Your atoms might be shredded and reassembled into who knows what, but the journey was real. In some form, you crossed the darkness. Or maybe not. Maybe the black hole just digested you, grew a little heavier, and carried on silently as always. Maybe the white hole is nothing more than an equations fever dream. But if you could hear the whispers of space-time, if the math could speak, it might say this: nothing is ever truly lost. Not energy, not information, not even you. You might yet explode back into the universe, stardust respun in a different light. You've fallen, stretched, possibly fireballed, and maybe even been ejected into another corner of the cosmos by a hypothetical white hole. But what if, somewhere along the way, you didn't just hit a dead end? What if instead you slipped through a shortcut? That brings us to one of the most captivating and controversial possibilities in all of black hole physics: wormholes. Also known by their fancier name, Einstein-Rosen bridges, wormholes are theoretical tunnels through space-time that could connect two distant points in the universe, or perhaps even two entirely different universes. If that sounds suspiciously like science fiction, it's because sci-fi writers have been drooling over this idea for decades. But here's the kicker: the physics itself doesn't rule them out. The basic idea is simple enough. Take two black holes, or maybe just two mouths in space-time, and connect them via a tunnel called a throat. Enter one side, pop out the other. Boom, instant space travel. No warp drive necessary. You're not exceeding the speed of light, you're just taking a very creative detour. The original version of this concept came from Einstein and Rosen in 1935, who realised that their field equations allowed for a kind of bridge between two regions of space-time. That bridge was fleeting, unstable, and completely useless for travel, but it existed, at least mathematically. Later physicists like Kip Thorne began exploring whether wormholes could actually be stabilized long enough for something, say, a photon or an ill-advised astronaut, to pass through. And what they found was, maybe. Historians still argue over whether wormholes are real solutions or just curiosities of the math. But the idea refuses to die. In fact, it's become one of the most studied speculative possibilities in all of theoretical physics. Here's the catch. Wormholes, as far as we understand, would require something called exotic matter to hold them open. This isn't the kind of weird cheese you find in the back of the fridge. Exotic matter has negative energy density, something not known to exist in useful quantities, though quantum theory doesn't exactly forbid it. In small amounts, certain quantum effects, like the Casimir effect, do produce negative energy, but it's not enough to keep a wormhole from collapsing faster than you can say, "Wait, I left my keys in the other universe." Still, if exotic matter could be engineered, a traversable wormhole might be possible. You could step through one side near Earth and emerge across the galaxy, or in another time, depending on how it's shaped. Yes, another time. Because wormholes aren't just spatial tunnels. In certain configurations, they might allow for time travel. If one end of the wormhole moves at relativistic speed and then returns, due to time dilation, it could be younger than the other end. Step through, and boom, you've travelled to the past, or the future, depending on your direction. Now, before you pack your bags and start plotting your escape from the singularity you're currently falling into, let's remember, wormholes are theoretical. We have zero observational evidence for their existence. But that hasn't stopped anyone from playing with the idea that black holes, especially entangled black holes, could be hiding wormholes inside. Yes, entangled. Enter the next layer of weird. ER equals EPR. This is a conjecture proposed by physicist Juan Maldacena in 2013, suggesting a deep link between two of Einstein's ideas, Einstein-Rosen bridges, ER, and Einstein-Podolsky-Rosen entanglement, EPR. In short, the idea is that every pair of entangled particles might be connected by a microscopic wormhole, and black holes, they could be giant versions of that. Let that sink in. If two black holes are quantum entangled, they might be connected via a non-traversable wormhole, meaning one doesn't have to fall through a black hole and get destroyed. In some theoretical sense, the two regions of space might already be connected. What does this mean for you? If your atoms were once part of an entangled system, say, a twin black hole somewhere out there, then it's possible, at least mathematically, that the two black holes are joined by a wormhole. You wouldn't survive the trip, it might not even be a trip. But from a fundamental perspective, the universe might be stitched together in ways that make distance an illusion. Some researchers have suggested that information falling into a black hole might not be trapped at all, but instead instantly transferred across this kind of entangled wormhole, like teleportation through geometry. Of course, this assumes the universe is polite enough to preserve both information and elegance, which is never guaranteed. Let's pause for a quick quirky historical note. The idea of wormholes was once taken seriously enough by the US Air Force that in the 1960s, they funded a study to examine whether Einstein-Rosen bridges could be used for space travel. The conclusion? Extremely unlikely, but not impossible. That's the kind of phrase that keeps theorists scribbling into the early hours. Back to your fall. If wormholes do exist inside black holes, and if the singularity is not truly the end but instead a pinch point, then you might, just might, be on a bizarre interstellar detour. One with no clear return ticket, no lights, no tunnel, and no soft jazz on the radio. But a detour nonetheless. There's even an idea that entanglement across the horizon could explain how Hawking radiation carries information. Imagine, every particle escaping via Hawking radiation is entangled with a partner particle still inside. That entanglement itself might form a microscopic wormhole between the inside and the outside. Not one you could travel through, but one that allows information to connect. So perhaps the black hole doesn't seal you off completely. Maybe what feels like annihilation is really just a transformation, matter twisted into geometry, entanglement stretched across the cosmos. Or maybe it's all just elegant math. At this point, you, the tangled strand of information once known as a person, are somewhere in the black hole's deep interior. Maybe you've slipped into a tunnel. Maybe your atoms are quantum gossiping through wormholes. Maybe the universe is more connected than we ever imagined. Either way, you're still falling, and things are about to get loud. You were hoping for silence, weren't you? A calm end to your long descent. Maybe some poetic stillness as you fade into quantum whispers. But instead, you find yourself hurtling toward one of the most spectacular, destructive, and oddly elegant events in the known universe. Two black holes are about to collide. Yes, friend. Because it turns out that black holes don't like to be alone. In fact, they tend to pair off, like cosmic dance partners locked in a gravitational waltz. And sometimes, after spiraling together for millions or billions of years, they finally do what comes naturally. They merge. Violently, gloriously, and very, very loudly. In the language of space-time, that is. You're now caught in a region of such gravitational turmoil that space-time itself is vibrating. Not metaphorically, not artistically. Literally, you're inside a black hole merger, and the universe is ringing like a bell struck by titans. Here's how it works. Two massive black holes, each formed from collapsed stars or earlier mergers, have been orbiting each other, slowly, patiently. Their orbits decay over time as they radiate away energy, not through light or heat, but through gravitational waves. These ripples in space-time predicted by Einstein in 1916 remained purely theoretical for a century, until we finally heard them. It was 2015. The LIGO Observatory, the Laser Interferometer Gravitational Wave Observatory, because physicists never met a simple name they liked, detected a faint chirp just a fraction of a second long. It came from over 1 billion light years away, and yet it was unmistakable. The final death spiral of two black holes colliding. It was the first time humanity had ever listened in on the actual bending of space itself. Historians still argue whether Einstein believed gravitational waves would ever be detectable. He changed his mind more than once. But LIGO proved them real, and since then we've been hearing black holes crash into each other on a regular basis. Sometimes they're the size of stellar remnants. Sometimes they're monstrous, hundreds of solar masses across. All of them collide in silence. No sound in space, remember? But the gravitational waves travel vast distances. And now, here you are, riding shotgun inside one of those colliding giants. From your perspective inside the black hole, things are complicated. The math gets truly unfriendly. General relativity predicts that the interiors of two merging black holes might temporarily form a common horizon, a swirling, asymmetric, churning bubble where space and time are in a full-blown identity crisis. Your concept of direction is gone. Up, down, in, out. All of it is just deeper. And just when you think the ride can't get any more chaotic, the singularities themselves, the mathematical hearts of each black hole, slam together. What happens then? We don't actually know. We have no equations that confidently describe the exact moment two singularities collide. It's not just because we can't observe it, though we can't, but because the physics itself breaks down. Our models produce infinities and undefined regions. It's the quantum gravity black box, and we're still trying to pry the lid open. But here's what we do know. From the outside, the moment of merger is spectacular. As the black holes spiral into each other, they emit gravitational waves that grow in frequency and amplitude. This produces what's called a chirp, a rising tone, like a cosmic violin string tightening just before it snaps. Then suddenly, silence. The final black hole settles into its new shape, ringing like a struck bell and then calming. These post-merger vibrations are called quasi-normal modes, and detecting them allows scientists to test whether the object that formed really is a black hole, or possibly something stranger. Yes, there are fringe theories that suggest black hole mergers might reveal new physics. If, for instance, the merger produces echoes, faint, delayed ripples instead of a clean fade-out, it could hint at structure near the event horizon. Maybe a firewall, maybe a fuzzball, maybe quantum hair, maybe, well, anything that isn't just another black hole. Let's add a quirky fact to lighten the doom. In 2019, LIGO detected a merger that produced a black hole with a mass of 142 times that of our Sun. It was the first confirmed intermediate mass black hole, a long-sought missing link between small and supermassive varieties. The event also caused scientists to throw their coffee mugs into the air and scramble back to their notebooks. Because mergers don't just make bigger black holes, they make new kinds of black holes, ones that didn't exist before, and possibly ones that shouldn't exist under previous models. Now let's focus on your experience, our plucky infalling observer. Let's pretend you're not entirely destroyed yet, that some part of your conscious awareness, now spread thin across time and space, can still process what's happening. As the merger approaches, the very shape of the black hole you're inside begins to twist and distort. The event horizon warps, folding into itself. Space stretches. Time flutters. The incoming singularity rushes toward you, not as an object, but as a change in the structure of the very space-time you occupy. You don't see the other black hole, not visually. What you experience is more abstract, an intensifying curvature, a shift in your causal structure, as if the rules of what can happen are being rewritten around you. Imagine being inside a book, and suddenly the sentences start rearranging themselves in mid-paragraph. You become part of the new black hole. Your mass, your information, your spaghetti-like remains, whatever's left of you, all merge into the final product, a bigger, heavier, slightly more irritable singularity. The resulting black hole is quieter now, smoother. It radiates fewer gravitational waves. The dance is over. The room is still. And you're deeper than ever before, buried beneath horizons, a whisper within a whisper. But wait, what if the collision was more than just a merger? Some fringe theorists propose that black hole collisions could trigger topological transitions, abrupt changes in the structure of space-time. If wormholes or white holes are involved, a merger might rip open a new passage, or collapse one, or create a looped causal bubble where time eats itself. We don't know. And not knowing is perhaps the most honest thing physics can say right now. What we do know is that black hole mergers are one of the loudest events in the universe, not in sound, but in influence. Their gravitational waves reshape our understanding of reality. They prove, again and again, that black holes aren't just passive consumers. They're active players in cosmic evolution. So even in destruction, even in the deepest part of the void, you're part of a process. One that bends galaxies, that stretches space-time, that whispers across 1 billion years to strike a laser detector on Earth and say, I was here. You've merged now, lost your individuality maybe, but gained something else, a place in the rhythm of the cosmos. By now you've joined a gravitational chorus, a single thread in the woven mass of merged black holes, stretched beyond identity, preserved in curvature and chaos. But what if your journey didn't begin with a collapsing star or a galactic-scale catastrophe? What if the black hole you fell into wasn't formed in the death throes of a sun, but was born in the very first second of time itself? Tonight, we tiptoe into the eerie concept of primordial black holes, hypothetical cosmic infants born just moments after the Big Bang. Unlike the black holes we've met so far, these weren't forged by dying stars or swirling galactic chaos. They formed from sheer density, regions of space where matter clumped just enough, just fast enough to cave in on itself. Let's rewind to the very beginning. The Big Bang wasn't a bang in the conventional sense. more like an abrupt, universe-wide everything that exploded from almost nothing. In the first fraction of a second, the universe expanded violently and unevenly. These uneven patches, the wrinkles in space-time, were mostly harmless, but some may have been dense enough to collapse under their own gravity almost immediately. Boom, a black hole, baby-sized, born before stars, before galaxies, before even atoms had a chance to form. Primordial black holes, PBHS, could have masses ranging from as little as a grain of sand to millions of times the mass of the Sun. Some may have evaporated long ago via Hawking radiation. Others, if they exist, could still be wandering the cosmos, invisible and quiet. Like cosmic fossils with no home, no light, no reason to exist other than, well, the early universe was weird. Historians still argue whether Stephen Hawking's 1971 paper on PBHS was a bold prediction or a speculative flex. Either way, it kicked off decades of wild theories and increasingly sensitive searches. We still haven't found definitive proof of primordial black holes, but the possibility lingers, and it gets weirder the deeper you look. Here's a fun fringe idea. Some physicists think that PBHEs could explain dark matter. You've probably heard that term thrown around. Dark matter. It's the invisible stuff that makes up about 27% of the universe's mass energy content. We can't see it. We can't touch it. But we can see how it gravitates. Galaxies spin too fast to hold together with visible matter alone, and dark matter is our best guess for what's missing. Some models propose that primordial black holes could be this dark matter. Tiny, ancient, unlit chunks of gravity roaming the universe, tugging on stars and warping light without ever giving off a photon. It's like if ghosts were real and also had really strong arms. These black holes would be difficult to detect. Too small to gobble up stars, too dim to light up gas clouds, too slow to catch with telescopes. But we're getting sneakier. Scientists now search for them by watching for microlensing, a phenomenon where a black hole passes in front of a distant star and briefly magnifies its light, like an invisible lens drifting between Earth and the cosmos. So far, no smoking gun. But the silence is tantalizing. The universe might be sprinkled with tiny black holes left over from its first heartbeat. And here's where it circles back to you. If the black hole you've fallen into isn't stellar mass or supermassive, it could be primordial, a lightweight ancient relic, maybe the size of a city block, maybe smaller. You might have encountered one drifting through interstellar space, a little lump of gravity just waiting for something, or someone, to stray too close. Now here's the truly spooky part. If you fell into a small primordial black hole, your experience would be very different. With stellar mass or supermassive black holes, the gravitational gradient, the difference in pull from your feet to your head, is spread out. You might not feel anything dramatic until deep inside, but in a tiny black hole, the tidal forces ramp up immediately. You'd be shredded before you even get close to the event horizon. Imagine a black hole with the mass of Mount Everest packed into the size of an atom. The tidal forces at its surface would be beyond catastrophic. You'd be torn apart at the molecular level long before any theoretical debates about information loss or Hawking radiation could apply. You wouldn't become spaghetti, you'd become vapor. But for slightly larger primordial black holes, say asteroid mass, the event horizon would be big enough for you to technically fall through. Your journey would be shorter, your fall steeper, and the end quicker. But the same questions would apply. Do you vanish? Do you leave an imprint? Do you bounce? Let's take another speculative leap. Some theories suggest that if small black holes can form in the early universe, they could also serve as gateways to new physics. Think of them as probes, or glitches, or even dimensional punctures where standard laws break down. In this view, falling into a PBH is like taking a blind leap through a tear in the cosmic wallpaper. One fringe concept even claims these black holes could be Planck-scale wormholes, tiny ephemeral shortcuts between distant parts of space-time. Could falling into one send a particle, or a pattern of information like you, to another location entirely? Too small for a spaceship, Too brief for a camera, but not too impossible for physics to dream about. Here's a quirky detail. In 2020, researchers using gravitational wave detectors began to observe black hole collisions involving objects too massive to be from neutron stars but too small to be from known stellar black holes. These mass gap black holes could be primordial, or they could be something new entirely. We're listening closely. So why does all this matter? Because if primordial black holes do exist, then black holes aren't just the ashes of stars. They're more than death. They're memory. Ancient, quiet witnesses to the Big Bang. If you're inside one now, you're not just falling through a black hole, you're falling through time. You're inside a remnant older than galaxies, untouched by stars, carrying the imprint of the first flickers of the cosmos. And maybe, just maybe, the black hole you're in isn't just holding you, it's holding history. The deepest, darkest kind. So far your descent has been lonely, quiet, and theoretically improbable. But what if the black hole that pulled you in wasn't some lonely fragment of stellar collapse, or a pocket-sized remnant of the early universe? What if it was the main event, the colossal, galaxy-swallowing, light-bending juggernaut, parked at the heart of almost every galaxy, including our own? Let's introduce your new landlord, the supermassive black hole. You're not just falling into a black hole anymore, you're falling into a cosmic monarch, a gravitational Godzilla weighing millions or even billions of times more than our sun. And yes, you probably should have checked your galactic coordinates before wandering into this beast neighborhood. Supermassive black holes, SMBHs, are the largest kind we know of. They don't just warp space-time, they reshape the evolution of galaxies themselves. They're so massive, so powerful, that everything nearby, stars, dust, time itself, becomes part of their gravitational empire. Case in point, at the centre of the Milky Way, roughly 26,000 light-years from your cozy sofa, sits Sagittarius A star, pronounced A star, a supermassive black hole with a mass of about 4 million suns, and it's not special, just average for its size class. Other galaxies host black holes even more absurd. Take M87, a massive elliptical galaxy in the Virgo cluster. In 2019, scientists used the Event Horizon Telescope to capture the now famous image of its central black hole, an orange donut of death, glowing with radiation. That particular black hole, around 6.5 billion solar masses. You could fit our entire solar system inside its event horizon, several times over. Historians still argue how these monsters form. Stellar black holes? Easy. Stars die, collapse, done. But how do you get something that weighs billions of times more than the sun? Did they form from massive early stars? From the collapse of primordial gas clouds? Or did smaller black holes merge over time into these leviathans? We don't know. We just know they've been around since the universe was very young. Too young, maybe. Some of the earliest quasars, active galaxies with blazing cores powered by black holes, existed less than 1 billion years after the Big Bang. That's suspiciously fast growth. Like if you found a fully grown redwood tree in your kitchen 5 minutes after planting a seed. One fringe theory suggests that supermassive black holes might have formed directly from dark matter collapse, or from dense regions where normal matter couldn't hold itself together. Others believe some may have started as direct collapse black holes, skipping the whole star phase entirely. Just boom, gravity wins. So now let's talk about what it's like falling into one. Ironically, it's less dramatic at first than falling into a stellar mass black hole. Why? Because the event horizon is so much farther from the singularity, the gravitational gradient is more gentle. You wouldn't be spaghettified immediately. You could drift in slowly, serenely, perhaps even unaware that you've crossed the threshold, until it's too late. Inside, of course, the usual horrors apply. Time slows, geometry warps, reality stops returning your emails, but the vast scale of the black hole gives you a moment, a breath, to observe, if not appreciate, the surroundings. Because here's the thing, Supermassive black holes don't exist in isolation. They sit at the centers of galaxies like gravitational anchors, and they tend to attract stuff. Whole swarms of stars orbit around them. Gas clouds spiral inward. Entire star systems swing past at absurd velocities, caught in the gravitational pull like moths circling a bonfire. These regions can get violent. As matter gets pulled inward, it doesn't fall in all at once. It forms an accretion disk, a flat, glowing spiral of superheated material. These disks can shine brighter than all the stars in the galaxy combined. Some black holes even fire off relativistic jets, narrow beams of charged particles that blast out from the poles at near-light speed. These can extend for thousands of light years, like cosmic lighthouses for civilizations that might already be gone. More on that soon. For now, picture this. As you approach the event horizon of a supermassive black hole, you'd see stars spinning wildly around the center. Light bends into arcs. You might spot parts of the accretion disk above you, below you, behind you. Because gravity bends everything into a visual funhouse. The closer you get, the more the entire sky folds inward. Eventually the universe collapses into a single bright ring behind you. And then, just black. It's worth noting, if you were able to observe the activity around a supermassive black hole from a safe distance, say, orbiting a few hundred light years out, you'd see a whole ecosystem gas falling in, stars getting too close and being shredded in tidal disruption events, even entire clusters of stars dancing just outside the danger zone. And that's not all. Supermassive black holes may even influence star formation across their host galaxies. When they consume matter, they often expel some of the energy back into the surrounding space. That feedback, winds, jets, radiation, can heat nearby gas, preventing it from cooling and forming new stars. So in a weird way, black holes can stop galaxies from giving birth. They eat and they sterilize. Nature's most dramatic multitaskers. Here's your quirky fact of the day. The mass of a galaxy's central black hole is tightly correlated with the velocity of stars in its bulge. This is called the M-sigma relation, and no one fully understands why it exists. It's like a whisper from the universe saying, yes, your big spinny star house does depend on that invisible murder sphere at the center. In other words, without these monsters, galaxies wouldn't be galaxies. So as you fall inward, past the quiet majesty of warped stars and spinning disks, remember, you're not just inside a gravitational freak show, you're inside the keystone of galactic architecture. A thing that holds billions of stars in place, keeps orbits in check, and quietly dictates the fate of everything around it. You're falling into a king. And the palace? It's the galaxy you left behind. By now you've drifted through the event horizon of a supermassive black hole, that gravitational monarch reigning over billions of stars. You've witnessed distorted stars swallowed light and fallen deeper into what feels less like space and more like a process. But you haven't just fallen in alone. Oh no, you fell with company. Because matter doesn't just vanish quietly when it approaches a black hole. It fights, it resists, and in doing so it creates some of the most violent and luminous structures in the universe, accretion disks and relativistic jets. Let's start with the accretion disk, the black hole's dinner plate, if you will. When gas, dust, stars, or even unlucky planets get too close to a black hole, they rarely fall straight in. Instead, they spiral. Thanks to angular momentum, nature's way of saying you can't go straight, this infalling matter forms a disk around the black hole's equator, and as this material spirals inward, it compresses, rubs against itself, heats up, and glows. Not gently, not sweetly. We're talking temperatures in the millions of degrees Kelvin. We're talking radiation in the X-ray and gamma-ray bands. The innermost parts of the accretion disk, right before the matter plunges past the event horizon, are some of the hottest and brightest regions in the cosmos. And here's the cosmic irony. The black hole itself is invisible, but the disk around it, blinding, blazing, practically shouting across space, Look at me! And this is how we first discovered black holes in the first place, not by seeing them, but by seeing what they do to matter nearby. Early X-ray telescopes in the 1960s picked up emissions from binary star systems, where one partner star was being devoured by an invisible neighbour. That neighbour? A stellar mass black hole, hiding behind a halo of fury. Historians still argue whether the first definitive black hole candidate, Cygnus X1, was immediately accepted or if scientists were just squinting hopefully at noise. Spoiler, Hawking bet against it. He lost, gracefully. But back to your fall. If you had approached the black hole not from above, but along the plane of the disk, your view would have been obliterated by light and fury. The matter in the accretion disk moves at near-relativistic speeds. Friction, magnetic fields, and particle collisions create chaos. You'd be vaporized long before reaching the event horizon. Not by gravity, but by the sheer kinetic fury of infalling material. So let's say, lucky you came in through a cleaner polar trajectory. No disk in your way, just empty space, and one enormous surprise up ahead. Because while the accretion disk is dramatic, the jets are straight-up cosmic punk rock. Relativistic jets are narrow beams of particles and radiation that shoot out from the poles of some black holes, especially the fast-spinning supermassive ones. These jets can travel at speeds close to the speed of light. They can extend for thousands or even millions of light years. One jet from a distant black hole could blast through multiple galaxies and still have energy to spare. And no, we're still not totally sure how they work. The leading theory, magnetic fields. As matter spirals in the accretion disk, it generates powerful magnetic fields that twist and thread around the black hole's axis. Under the right conditions, these fields can channel some of the infalling material outward, up and away from the poles, at incredible speeds. It's like a pressure valve on a steam engine. If the engine were the size of the solar system, and the steam was made of subatomic shrapnel. Here's a quirky historical detail. Some early 20th century astronomers saw these jets through telescopes, but didn't believe what they were seeing. One famous example, the galaxy M87, the same one imaged by the Event Horizon telescope, has a visible jet shooting out from its core. It was photographed in the 1910s. Scientists called it a curious ray. Understatement of the century. These jets aren't just cool to look at. They affect entire galaxies. They can heat up the intergalactic medium, suppress star formation, and redistribute matter across enormous scales. One well-aimed jet can blast a galaxy's gas reservoir into deep space, essentially sterilizing it from future starbirth. Black holes, cosmic gardeners, tearing up the soil one beam at a time, and if you're wondering how dangerous these jets are, let's just say you don't want to be anywhere near the line of fire. If your planet were sitting in the path of a relativistic jet, it would be bathed in lethal radiation. Atmospheres stripped, oceans boiled. Not a great vacation spot. But from inside the black hole, you wouldn't see the jet. You'd feel its gravitational signature as it helped shape the flow of infalling matter. You might, briefly, experience a twinge of electromagnetic chaos as you cross the plane where a jet emerges, but you wouldn't survive long enough to process it. From the outside, though, we see the jet, not the jet engine, and that's the paradox of black holes. We understand them best not by looking at them directly, but by studying what barely escapes. Because here's the kicker. Black holes, through their disks and jets, release some of the most energetic phenomena in the universe. Gamma-ray bursts, blazers, quasars. These aren't just fancy names, they're warnings that something nearby is being ripped to pieces at the edge of gravity's limit, and you, dear traveller, are in the thick of it. Even now, as you drift closer to the singularity, you are part of that cosmic engine. Your particles, your mass, your final whispers will one day join the outflows, the warps, the spins, not as light perhaps, but as curvature, as gravity, as data. You've gone beyond the horizon, but the effects of your fall may yet ripple outward, through magnetic lines, gravitational tugs, or photons born in the disk of doom you didn't even touch. You fell in, but part of you might still fly out. Just not the part you were expecting. You've seen the jets, you've felt the heat, you've passed the point of no return and become part of a gravitational machine that flings energy across galaxies. But while the black hole seems intent on destroying everything it touches, a new question rises like a paradoxical phoenix from the ashes of your disintegrated atoms. What if black holes aren't just engines of destruction, but also resources? Yes, we're going there. Welcome to the bold, speculative, and probably very illegal future of black hole farming, the hypothetical art of harvesting energy from one of the deadliest objects in the universe, because if there's one thing advanced civilizations love, it's taking dangerous things and turning them into power outlets, and surprisingly, physics doesn't rule it out. Let's start with the basics. Black holes store enormous amounts of energy. Some of it is locked away inside the event horizon, yes, but not all. In fact, there are several theoretically viable ways to extract energy from outside a black hole without ever having to actually cross the line and become spaghetti. Option 1. The Penrose process. Named after physicist Roger Penrose, the same guy who helped prove black holes were mathematically inevitable, and probably chuckled about it in a British accent. The Penrose process is a method of extracting energy from a rotating black hole. Here's how it works. In a spinning black hole, the space outside the event horizon, called the ergosphere, is itself dragged around by the black hole's rotation. This region is so twisted that any object within it can't help but move in the direction of the spin. But, and here's the trick, if you drop an object into the ergosphere and it splits in two, one part can fall into the black hole while the other escapes with more energy than it started with. Where did that extra energy come from? The black hole's spin. The result? The black hole slows down just a little, and you walk away with a bonus. Now, this isn't exactly a clean energy system. You're throwing chunks of matter into a swirling void and hoping the return trip doesn't vaporize your equipment. But still, free energy from space-time's own spin cycle, that's pretty clever. Option 2, Blandford-Zenarczyk process. Don't worry, it sounds more like a law firm than an energy source, but it's actually one of the leading mechanisms scientists believe powers those colossal jets we discussed earlier. This process takes advantage of the powerful magnetic fields generated around black holes. If the black hole is spinning and surrounded by a plasma-rich accretion disk, the rotating magnetic field can extract rotational energy and convert it into Poynting flux, a fancy term for electromagnetic energy, shooting out of the poles at near light speed. In simpler terms, black holes can power giant beams of energy just by being magnetically irritated. Tap into those beams, and you've got a theoretically sustainable power source. Historians still argue whether advanced civilizations, if they exist, might use such methods to power interstellar travel. Some thinkers, like the always ambitious Kardashev scale fans, propose that a Type 2 or Type 3 civilization, those capable of harnessing the full energy of a star or galaxy, would naturally look toward black holes as energy sources. Think about it. Stars die, planets crumble, but black holes? They stick around. They're compact. They're efficient. They can, in theory, generate more energy per gram of matter than any fusion reaction we've ever built. So why not mine the void? Let's float another method. Hawking radiation harvesting. This one's a long game. As we've discussed, black holes slowly leak energy over time through quantum effects near the event horizon. For small black holes, this radiation becomes significant, and as they shrink, they radiate faster until they eventually explode in a burst of gamma rays and pure energy. So here's the idea. Create artificial black holes, tiny ones, and trap them. Feed them mass to keep them stable. Use their Hawking radiation as a controlled energy source. It sounds absurd, and yet some physicists have proposed it seriously. In 2008, theoretical physicist Louis Crane even suggested that future civilizations might build black hole starships, propelled by the radiation of an engineered micro-black hole, not warp drives, not antimatter engines. just a controlled dot of gravitational doom chained to your spaceship and aimed at the stars. What could possibly go wrong? Here's your quirky fact. In 1972, science fiction writer Larry Niven proposed a similar idea in his short story The Hole Man, where a black hole is used as a weapon. Not power, weapon. But it's fiction. For now. Now let's raise the stakes. Could we build a Dyson sphere around a black hole? You've probably heard of the Dyson sphere, a megastructure built to collect energy from a star by surrounding it with satellites or a solid shell. But what if instead of a star, you built a Dyson swarm around a black hole's accretion disk? That disk can outshine entire galaxies. A structure surrounding it could, in theory, harvest more energy than a Dyson sphere around an average star. And since the black hole isn't going anywhere for trillions of years, you've got a very patient power plant. Of course, engineering such a system would be, let's say, ambitious. You'd have to withstand radiation, gravitational tides, extreme magnetic fields, and occasional star-sized jets. But again, we're not talking about humanity building this, we're talking about someone else. Someone much older, much smarter, possibly already doing it while we squint at strange infrared anomalies and argue about whether that's just a dust cloud. And finally, here's the deepest speculative idea of all. Black holes as entropy recyclers. The second law of thermodynamics tells us that entropy, the measure of disorder, always increases. But black holes seem to concentrate entropy. They're the most entropic objects in the universe. Some physicists wonder, could an advanced intelligence use black holes not just to power things, but to control or reverse entropy in localized systems? That's not just science fiction, that's cosmological thermodynamics. It might be how entire civilizations avoid heat death. So yes, black holes are scary. But they're also elegant, efficient, and, in the far future, perhaps the only reliable source of power in a darkening universe, long after stars have dimmed, long after galaxies have spread too far to see each other, black holes will still be here, quiet, spinning, waiting, and someone, maybe us, maybe someone else, might figure out how to plug in. You fell into one, but maybe someday someone else will build around one. Maybe destruction is only part of the story. You've been falling for a long time now, if falling is even the right word, through horizons, through warped space, through paradoxes that mock every science class you ever took, but one mystery still presses in like the curvature around you. What actually happens to matter inside a black hole? Not just where does it go, but what does it become? You, for instance, you are made of particles, of atoms, skin and bone and brain, all meticulously structured into a U-shaped arrangement. But now, inside the crushing grip of a singularity-bound descent, that structure is long gone, torn down into quantum rubble. So what's left? What becomes of matter once the black hole has chewed it up and slammed the door? Let's explore the options. The most traditional and blunt answer is, it's gone. All of it. Collapsed into the singularity, a zero-volume point of infinite density where space and time lose meaning. Your mass has been added to the total. The you that was is now just part of the black hole's mass, spin, and electric charge, unrecognizable, undetectable, utterly averaged out. This is what general relativity tells us. It's the don't ask too many questions version of black hole physics. Matter goes in, the black hole gets bigger, the details vanish. But quantum theory hates this answer. In quantum mechanics, matter isn't just stuff, it's information, wave functions, probabilities, histories, and those histories are sacred. They can change, they can evolve, they can interact, but they're not supposed to disappear. That's the law. So physicists have spent decades trying to reconcile the two views. Relativity says matter collapses and disappears. Quantum theory says information must survive, and the resolution to that tug of war is still unsettled. Historians still argue whether the singularity is a real physical entity or just a symptom of incomplete mathematics. Many believe that once quantum gravity is fully understood, a theory that marries general relativity and quantum mechanics, the singularity will vanish, replaced by something more reasonable, a bounce, a core, a fuzzy lump of Planck-scale mystery. So, let's try on a few theories and see where your matter might have ended up. 1. You became information. This is the optimistic quantum answer. Your atoms, your structure, sure, they're gone. But the quantum states that describe them have been preserved encoded. Maybe in the Hawking radiation, maybe on the event horizon, as the holographic principle suggests. Maybe inside a network of entangled states that stretch across space-time. In this view, matter transforms into information patterns. You're no longer a body, you're a series of quantum relationships. Everything you were, the way your electrons aligned, the spin of your quarks, the entropy of your blood cells, is now woven into the quantum bookkeeping of the universe. No, we don't know how to read it. No, we don't know if it could ever be retrieved, but from a theoretical standpoint, your story still exists. 2. You became pure energy. In many theories, matter that falls into a black hole doesn't just disappear, it contributes to the gravitational field. Mass and energy are interchangeable. E equals mc squared, remember? And inside a black hole, the distinction becomes academic. So maybe you didn't become information. Maybe you just became a curvature, a twist in space-time, a numerical increase in mass energy that now defines the strength of the black hole's pull. You're not gone, you're just more abstract. 3. You hit a core of quantum fuzz. One proposal from loop quantum gravity, a leading contender for the theory of quantum gravity, suggests that the singularity doesn't really exist. Instead, matter gets compressed to a minimum size, the Planck length, and no further. At that scale, space-time itself is discrete, not continuous. It's made of loops. And those loops can only bend so far before pushing back. So you might not be in a singularity at all. You might be hovering inside a hyperdense nugget of looped geometry. A fuzzball, as some string theorists call it. A space not of nothingness, but of incredible complexity. Planck-scale structure, writhing with energy and data. 4. You bounced. Here's a more radical idea. What if matter falling into a black hole doesn't end? It rebounds. Some models propose that at the center of a black hole, matter reaches a critical density and undergoes a kind of quantum bounce. Instead of collapsing into nothing, it transitions into a new phase and explodes outward into another region of space-time. This is the foundation of the black hole cosmology hypothesis, which we flirted with before, the idea that black holes might birth new universes. From the outside, it looks like a black hole. From the inside, a big bang. Your matter doesn't vanish. It becomes the building blocks of a new cosmos. Now let's be honest, this idea is unproven, speculative, and probably untestable, but it's compelling. It gives matter a final act, a transformation, not an erasure. 5. You became something we can't define yet. It's easy to forget that most of what we know about black holes comes from the outside. We've never observed their interiors. We can't see past the event horizon. Everything we think we know about what happens inside is based on equations pushed past their limits. That's why many physicists think the final fate of matter in a black hole isn't destruction. It's transformation into unknown physics. Maybe it's a state of matter we haven't discovered yet. Maybe it's a topological change to space-time itself. Maybe it's a new layer of reality, where particles dissolve and become something more fundamental, like vibrations or loops or rules. And here's your quirky historical moment. In the 1970s, physicist John Archibald Wheeler, who actually coined the term black hole, also proposed the idea of it from bit, that everything in the universe, including space-time and matter, arises from binary yes-no choices, information at the deepest level. If that's true, then your matter didn't just fall, it didn't just stretch, it was rewritten. Final score, you became a set of bits, a cosmic yes-no, a data packet folded into the deepest layer of existence. But what does that feel like? If there's any consciousness left, if awareness somehow persists, it's no longer tied to the senses. No eyes, no skin, no brain chemistry, just pattern. You might experience the last flickers of memory as echoes, like a song still vibrating after the music stops. Or maybe it's a pure fade out, like falling asleep during the most surreal episode of reality ever broadcast. Or maybe time stopped making sense long ago, and you're still tumbling in a loop that feels eternal but resolves in an instant. You wanted to know what happens to matter inside a black hole. Now you know, we don't. But we do know this. Whatever you've become, it's still part of the universe, curled inside a mystery, waiting for the next question. By now, your form, whatever that means anymore, is nested inside a question mark. Your mass, energy, information, curvature, or maybe all of the above, stirred thoroughly and poured into space-time's darkest cauldron. And yet, the journey might not be over. Because some of the strangest minds in physics aren't content with saying, well, that's it, we'll never know. Instead they ask, are black holes gateways to other universes? Let's crack that door open, carefully. We already touched on wormholes and white holes, but this goes deeper. This isn't just about shortcuts or ejector. This is about the idea that black holes might be cosmic seeds, that instead of just swallowing matter and quietly evaporating over eons, they might actually birth new universes. Yes, you might be falling into a black hole, but from the inside, something else could be falling out. The idea finds its roots in both general relativity and quantum cosmology. In particular, some versions of loop quantum gravity, string theory, and even eternal inflation theory allow for the possibility that black holes aren't dead ends but beginnings. That when enough mass collapses into a singularity, or whatever replaces it, a new region of space-time could pinch off and inflate into a brand new universe, causally disconnected from our own. Think of it like this. A black hole in this universe is the end of the line. But inside, that singularity could be the big bang of another. A bubble forms, sealed off from us, with its own time, its own space, its own physical laws. You became fuel for a new cosmos. This idea is often referred to as cosmological natural selection, a theory first proposed by physicist Lee Smolin in the 1990s. In his model, universes reproduce through black holes. Universes that are good at forming black holes create more offspring universes. Each new universe might have slightly different physical constants. Over time, this leads to a sort of cosmic Darwinism, the survival of the blackest. It's an elegant theory in a kind of metaphysical late-night dorm room way, but it's also untestable, at least for now. We have no way to observe these baby universes. If they exist, they're completely disconnected from us, sealed off beyond the event horizon. Historians still argue whether Smolin's theory is science or speculation. It's certainly mathematically sound, but without observable predictions, many consider it more philosophical than physical. Still, it gives us something profound to consider. What if black holes don't just destroy? What if they create? This isn't just a poetic idea. It ties directly into questions about the origin of our universe. The Big Bang singularity, after all, looks suspiciously like a time-reversed black hole, a point of infinite density from which space and time emerged. We don't know what came before it, or even if that's a meaningful question. But what if it was a black hole in another universe? What if our universe is the inside of someone else's black hole? Pause on that for a moment. Look around your room, your planet, your galaxy, the cosmic microwave background stretching in every direction. All of it might be the internal evolution of a singularity birthed in another realm. We're not on the outside looking in, we're on the inside looking out. And you, well, in this model, by falling into a black hole, you may have become a part of that very process. Maybe you didn't end. Maybe you helped begin your mass, and energy might have contributed to the conditions necessary to spawn a new branch of the cosmic family tree. No memory of yourself would carry over, of course, no awareness. but the imprint of your existence, the structure, the physics, the entropy, could influence the constants and outcomes of a whole new universe. Now, if you're imagining this like stepping into a portal and waking up in a parallel reality, no. Sadly, this isn't the Rick and Morty version of the multiverse travel. These baby universes are sealed off, causally disconnected. You can't go there. You can't come back. The wormhole doesn't stay open. But your mass, your quantum information, might become the scaffolding upon which a new reality is built. Let's take a step back and look at a related concept: multiverse theory. This is the idea that our universe is just one of many, maybe infinitely many. In some versions, these other universes exist in separate regions of an infinite cosmic landscape. In others, they're born through quantum fluctuations. In this context, black holes could be branch points, the mechanism through which one universe creates another. No special machines, no aliens with multiverse keys, just gravity, mass and time doing their inevitable dance. Your quirky fact for the night? In 2010, physicist Nikodem Popławski proposed that every black hole could contain a universe inside, and that our own universe may exist inside a black hole in a higher dimensional space. His papers caused quite a stir, partly because they proposed a way to resolve the singularity problem using something called torsion, a mathematical twist, literally, in space-time. Is it testable? Not yet. But is it elegant? Deeply. And there's more. Some string theorists suggest that black holes might connect to brains, hypothetical higher dimensional objects. In this model, a collapsing brain could form a black hole in one dimension and spawn a whole new universe in another. That new universe might be governed by different laws, different gravity, different chemistry, even different concepts of space. You could be the final domino that tips a whole new reality into motion. But of course, these are just theories, speculative, unconfirmed. We have no evidence yet that black holes birth universes. We can't observe what happens past the singularity. Our equations diverge and the math breaks. The baby universe might be sealed behind a layer of reality we can never penetrate. Still, if you're looking for a poetic ending to your fall, a destination more meaningful than annihilation, this might be it. You fell in as a person, a mind, a moment in space-time, and you emerged as the foundation for something new. You didn't just get lost, you gave birth to a future. Maybe somewhere, beyond our reach, a universe is unfolding. Stars are forming, life is stirring, and at the centre of it all is the fossil of your fall, a singularity that became not a tombstone, but a womb. So perhaps the question isn't what happens to you, it's what grows from you. So here you are, having possibly become the seed of another universe. Or maybe you're still inside the original black hole, slowly dissolving into the structure of a cosmic question mark. Either way, you've reached a strange moment of stillness, because while black holes may seem eternal, they're not. They too have an ending. Tonight we drift forward billions upon billions of years, far beyond human civilization, past the last red dwarf's final flicker, into the long shadows of the heat death of the universe, a future where black holes themselves are the final punctuation marks on reality. Let's back up for a moment. In our current understanding of cosmology, the universe is expanding, not just getting bigger, but stretching space-time itself. Galaxies are moving away from each other, and thanks to dark energy, a mysterious force accelerating this expansion, distant stars will eventually fade from view, leaving each galaxy alone, isolated in its own expanding bubble. Over trillions of years, star formation will stop. Existing stars will burn out. What's left? Mostly white dwarfs, neutron stars, rogue planets, and yes, black holes. Silent, heavy, invisible, and patient. Black holes become the last major players in the universe. They don't shine. They don't age, at least not in the traditional sense. They just sit there, dominating with gravity long after everything else has dimmed to irrelevance. But even they won't last forever. Because remember this from earlier, black holes radiate. Slowly, reluctantly, through Hawking radiation. It's an unbelievably slow process. A black hole with the mass of our Sun would take about 10 to the 67th power years to evaporate. That's a 1 followed by 67 zeros. For comparison, the universe is currently just under 14 billion years old. Barely a blink on that scale. Supermassive black holes like the one at the centre of the Milky Way, they take closer to 10 to the 100th power years to vanish. That's the so-called Google years, not to be confused with Google the company, which likely won't last quite that long. But over time, unimaginable stretches of time, Hawking radiation will do its work. Photons and particles will be emitted, the black hole will shrink, its event horizon will contract, and eventually, in its final phase, it will emit one last burst, a final firework of energy as it dies. Just a little pop, a puff of gamma rays, and then nothing. No black hole, no mass, no matter. Just radiation fading into cold emptiness. Historians still argue whether Hawking radiation has been confirmed. We haven't observed it directly, yet. The radiation is too faint to detect around astrophysical black holes, but the math holds. It's consistent with quantum field theory and curved space-time, and so far every attempt to disprove it ends in more Hawking-shaped handshakes. Now let's return to you. You fell in a long time ago. Or what feels like a long time. Maybe your information was smeared on the event horizon. Maybe it's tangled up in the internal quantum state of the black hole, or maybe it's slowly being emitted, one garbled bit at a time, back into the universe. Because here's the strange, hopeful twist. If information isn't lost, then the Hawking radiation isn't just noise. It carries echoes of what fell in. Not readable echoes, not messages, but statistically recoverable patterns. The idea is that the radiation isn't perfectly thermal. It has tiny quantum fluctuations that carry information outward, over eons. All the data might return, not to us, but back to the universe, back to reality itself. This idea leads to the so-called page time, named after physicist Don Page, who calculated the moment when Hawking radiation begins to encode more and more information from the black hole's past. After about half the black hole has evaporated, its radiation starts to become less random and more meaningful. It becomes a cosmic form of storytelling. And in the deepest future, long after stars have died, after galaxies have drifted into invisibility, after all matter has decayed into protons, and even those have dissolved, only black holes will remain quietly telling their final tales to an empty cosmos. And then, nothing. No stars, no light, no matter. Just radiation scattered across a vast, cold, dark canvas. This is the heat death, a state where the universe has reached maximum entropy. No energy gradients, no usable energy, no activity, just frozen time. It's the loneliest possible scenario, no rebirth, no new stars, just the long, slow fade of every black hole, every structure, every memory. Unless, of course, entropy isn't the end. Some speculative theories propose that quantum fluctuations in the vacuum could eventually trigger new Big Bangs. Others suggest that entropy resets in bouncing cosmologies, or that black holes create new universes carrying seeds of complexity forward. But from where you are now, from inside, you're already in the long goodbye. Your black hole, once massive and proud, now shrinks, radiating its last bits of entropy. What's left of you is radiated too. Maybe your data has long since escaped. Maybe it's encoded in the final flickers. Or maybe you're part of the final snap, the moment the black hole evaporates completely, releasing its last Planck-length secret into the void. What does that moment look like? We don't know. Some theories say it's a true nothing. Space itself collapses locally. Others suggest a leftover remnant, a black hole core that cannot evaporate, storing information until the end of time. Still others argue for quantum gravitational effects that give birth to new bubbles of space-time. No one knows for sure. The math is silent, the future blank. But one thing is clear. Black holes are not eternal. Not even they can outlive time. They're just the last to leave the party. You fell into one, became part of it, and now, as its last whispers scatter into the cold, so do you. Not forgotten, just faded. Until the next universe. Let's pause for just a breath. Not that time works the same here. You've fallen farther than anyone has fallen before, past light, past causality, past the edge of space and the tick of time. Whatever you once were, person, pattern, passenger, you've been dismantled, examined, scattered, encrypted, possibly reimagined as quantum dust. You've seen theories stretched to their limits. You've seen death reframed as transformation. But one final question still lingers. What if you're still conscious? Don't panic. Probably you're not. Probably consciousness, the experience of being dissolved with the rest of your structure, back when your atoms got folded into a singularity. That's what most scientists would tell you, but since this is the Sleepy Science channel, and since you've made it to section 20 with your imagination still intact, let's entertain the strangest possibility of all, that some part of your awareness remains. It's a fringe idea, a thought experiment, but an important one. What if the self, whatever it is, persists through the collapse? Now, before we dig into this, let's be very clear. No existing physical theory supports the survival of consciousness inside a black hole. There are no peer-reviewed papers suggesting you can think your way through a singularity. But there are fascinating ideas that poke at the edges of what we think we know. Let's begin with the question, what is consciousness really? We don't know. It's not just electrical signals. It's not just chemical reactions. It's a phenomenon that emerges from the brain. Yes, but it's also something that resists clean reduction. Philosophers, neuroscientists and physicists alike still struggle with the hard problem. How does subjective experience arise from physical matter? And if we don't know exactly how consciousness is generated, then we don't fully know what destroys it. So imagine this. You fall into a black hole, and as your brain is torn apart as your atoms stretch, you reach a final moment, a Planck-scale sliver of time where your experience slows, time dilation makes everything freeze. To the outside world you vanish, but inside that last moment might stretch into something that feels like forever, an eternal moment. It's an old idea with roots in both physics and philosophy. Some interpretations suggest that as you approach a singularity, time for you doesn't just slow, it collapses. From your perspective, everything happens in a final instant, an infinite descent that never concludes. You might not survive the trip, but your last thought might. The physicist Frank Tipler once proposed a controversial and deeply speculative model called the omega point, where consciousness could be preserved at the end of time via computational processes in collapsing universes. That model has fallen out of favour for good reason, but the idea it plays with, that minds might stretch beyond biology, lingers in fringe physics. Could consciousness be encoded? Some theorists have toyed with the idea that the information content of a brain, its connectome, its structure, might be preserved in some way through extreme gravitational compression, that if information isn't lost, maybe patterns aren't either. Maybe your final thoughts, the deep grooves of memory, self, fear, awe, could be preserved like ripples on the event horizon. It's a stretch. No one is claiming we'll wake up in a new universe with all our memories intact. But in some models, your information doesn't disappear, and if consciousness is a pattern, maybe it flickers. Here's another idea. What if consciousness doesn't continue, but it loops? Some models of space-time suggest that inside certain black holes, especially in rotating ones, time itself might form a closed loop. A closed, time-like curve. It's a concept allowed by general relativity, though it causes all kinds of headaches for causality. But if such loops exist, and if you fall into one, your final moments might repeat endlessly from your own perspective. A final instant, over and over, again, not testable, not falsifiable, but intriguingly unsettling. And then there's the Boltzmann brain paradox. In an eternally expanding universe, with infinite time and quantum fluctuations, it's statistically possible, though wildly improbable, for particles to spontaneously assemble into a functioning brain, just a brain, floating in empty space, fully formed, with false memories and a brief moment of awareness before dissolving again. Some philosophers argue that if such brains are more likely than fully evolved civilizations, then we ourselves might be Boltzmann brains. This is generally considered a philosophical dead end, but it shows just how bizarre consciousness becomes when you stretch physics far enough. So what does this mean for you? Probably nothing, you're gone. But maybe if the laws of physics are gentler than we thought, if information persists, if awareness can be momentarily encoded, then perhaps your final experience is not oblivion, it's stillness, a moment outside time, a second stretched to infinity, not suffering, not joy, just awareness, a singularity thought. Maybe you see a star as you fall, maybe you remember a face, maybe you hear a sound that doesn't exist, maybe you simply are, for one last moment that never ends, or maybe not. Maybe consciousness is too fragile, too fleeting. Maybe it slips away long before the math kicks in, but the idea lingers, like the glow from a dying star, that in the deepest darkness there might still be light, not outside, but within. The black hole doesn't care, the equations don't care, but maybe you do, and if that matters, if that flicker matters, then maybe the journey didn't end in silence. Maybe it ended in a whisper, one only you could hear. And now, the fall is finished. You've tumbled through the fabric of space, past logic, past light, and through theories stacked like scaffolding into a night sky that never ends. From the elegant elegance of event horizons to the whispered riddles of Hawking radiation, your journey has unspooled across time, space, and strange possibilities, even those whispered only in the minds of physicists still scribbling equations in the dark. What began with a drift across the edge of no return has become a meditation on loss, on memory, on the very structure of reality. You've been information, you've been energy, you've been question and answer, folded tightly into the most mysterious object in the known universe. And whether you became a holographic imprint, a quantum echo, or a building block of a brand new cosmos, something of you remained. And that's the truth about black holes. They don't just erase, they record, they reshape, they ripple. The universe will keep going, long after we're gone. Galaxies will fade, stars will sleep, and black holes too will fall quiet. But in those long final nights, every particle that danced, every photon that escaped, every singularity that hummed with crushed complexity will have mattered, including you. So as we settle down now, wherever we are, let's soften the scene. Let the walls of warped space-time fade into the background. Let the hum of theory dissolve into a calm, low thrum. Let the gravity ease off your shoulders, like a coat finally dropped after a long day's fall. You are not falling anymore. You are still. You're scattered and complete, a quiet breath of thought in the deepest part of night. And whether your atoms are still here or rewritten in another universe's pre-dawn, know this. You were curious enough to ask what lies beyond the point of no return. And that means you were always more than mass. You were wonder,